Okay, well, we are back to actually the original semester that I was in here for this. And so the skills we're looking at, the big skill this semester, and for most semesters, is what we call evaluating a formula. So if we're given a formula for a specific calculation, we need to be able to take numbers that are given from a situation and plug them into the formula. So one of the formulas we're going to look at is the formula for, it's a little bit high. There we go. Is the formula for work. So work, we're going to abbreviate that with a W, is equal to a force applied times a distance moved. So we're just going to abbreviate those with the F and D. Now, the one thing that we have to make sure we clarify here is that both the force and the distance have to be in the same direction. So if we take a 150-pound weight and we drag it across the floor, we haven't technically done any work against the weight of that object because the weight is pulling down. In order to do work, we would have to oppose that force. We would have to lift upward. As we're pulling in this direction, the only force we're resisting is any sort of friction between that weight and the ground. So the work would have to be calculated based off of the force of friction. So in order to do work with that 150-pound weight, we're going to lift that 150-pound weight up to a height of 60 feet. So whether this is some sort of an elevator or a hoist or whatever, the amount of work done then would be just the weight, 150 pounds, times the distance of 60 feet. Of course, 150 times 60 is going to be 9,000. Oops, no extra charge for the extra zero. Now, for you guys, it depends on what textbook you use. Some of your textbooks, I know, list this as pound-feet is the units on this. Others listed as foot-pounds. They're the same unit. It's a little awkward for me to hear pound-feet because I've always heard foot-pounds. I don't know what's happening there. Is it's the heater? I know the heating unit is right next door here, so I don't know if that's one of the valves for the heating and AC unit or whatever. But, well, anyway, I was always taught that units should be put in alphabetical order, so foot-pounds, but either unit is acceptable there. Another common formula that applies is density. So this is one that we tend to mess up. Density is equal to mass, M, over volume, V. In the customary units, we used to call them standard units, but now we have to refer to them as U.S. customary because they're starting to refer to metric now as standard. In customary units, we mess up this calculation because we don't use mass, we use weight. And there is a difference between them. Mass is the amount of matter in an object. Weight is the force of gravity on it. If I take that object to the moon, it weighs less because there's less gravity, but it still has the same mass. But let's say we have an object that is 40 cubic inches in volume, or in volume, and weighs 30 pounds. Its density, we'd put in the 30 pounds as the mass, in this case weight, over the volume of 40 cubic inches. So we divide the numbers. 30 divided by 40 is 0.75. Now here's an example where we combine the units as well. Up here we multiplied, we combined the units. Feet times pounds became foot-pounds. Down here, pounds divided by cubic inches is pounds per cubic inch. Now, like I said, technically, in the metric system, it would be kilograms, which is a true mass measurement. Anybody know what the mass unit is in the standard measuring system? It's one that some of you may have heard but didn't realize it was an actual unit of mass. It's called the slug. A slug is 32 pounds. And it was the amount of matter that has a weight of 32 pounds on Earth. You ever heard the phrase, there's a whole slug of them over there, or we have a whole slug of those? That's where that comes from. It's a pretty big unit. Outside of engineering, I've never seen it actually used for anything. Kind of, yeah. Is anybody here, any of the companies you guys work for are actually using the metric system exclusively yet? So yours is? Where do you work? Okay. A lot of companies that do international work are moving over to doing everything in the metric system, even the part that's done in the U.S., because they're figuring it saves a lot of money. IBM did this 7 or 8 years ago. In the first year, they figured it saved like $8.5 million because they didn't have to, when they did all their blueprints, they didn't have to convert all the measurements to both units. Less waste because sometimes there's slop in the conversions. It doesn't give you an exact conversion, so you got parts that don't quite fit perfectly.
So with Volkswagen,
Mm-hmm.
why did they switch to the metric system?
Well, Volkswagen, of course, is out of Germany, and so they're producing. So they were already metric, but they have a lot of their production facilities in the U.S., so they were using U.S. customary because a lot of their employees were familiar with it. They just decided to make the full switch even in the U.S. just because their engineers, everything was designed and engineered in metric system in Germany. So sending it over here, they had to spend money to convert everything. So
That's everything that we work on.
okay,
Always.
always VW.
Yeah,
Sure.
German or metric.
Sure.
Obviously,
Yep. A lot of people are nervous about the metric system, and I get it because we're so used to the customary system. But once you get to know the metric system, it is so much easier to use. So the customary system was what they called an evolved system. There was a need to measure something. They came up with a way of measuring it. If I wanted to measure how long this piece of paper was, well, they used your thumb. They measured your 1, 2, 3, 4, 5 inches. If they wanted to measure how wide the room was, they put their feet end to end. But there was never any intention of those units to be used together. It was literally hundreds of years after they started using them that they said, well, it'd be nice if you measure something in inches and I measure something in feet. It'd be nice to be able to tell which one's bigger. Originally, somebody had to go back and remeasure in the other unit was the only way they could compare. So that's when they came up with, well, let's adjust the sizes so that 12 inches fit a foot, 3 feet a yard. That's why all the conversions are horrible. A gallon is 231 cubic inches or 7.48 gallons in 1 cubic foot because they were never designed to work together. In the metric system, they had used customary measurement for a couple thousand years. So they sat down when they developed it. They did this in the late 1800s. In Switzerland, actually, it was developed. They knew all the things that worked well with customary measurement, and they knew all the things that were a struggle, like all the weird conversions. So they designed a system that got rid of all the struggles, like all the strange conversions. Everything's a multiple of 10, and kept the things that worked well. Like in the metric system, 1 cubic centimeter is equivalent to 1 milliliter, and 1 gram is 1 milliliter of water. So you can convert from volume to capacity to mass really quickly because everything is set up to convert real easily. It's just going to take some time to get used to it. Anyway, I went off on a tangent there. By the way, the metrics, one of the things I always question with the metric system is you have a yard that's this long and a meter that's this long. Why was that? Why didn't they just make them the same? The customary, they used to call it the standard system, was anything but standard. King Edward declared so the yard was the distance from the center of your chest or the point of your nose to the end of your outstretched arm. King Edward declared that his his yard was going to be the official yard. Different kings in different areas did the same thing. So the Swiss king had done the same thing. Well, the Swiss yard was longer than the Swiss king was taller than King Edward. So the metric meter is actually a yard. It's just not the U.S. yard. It was the Swiss yard. Yeah.
Paces. How many paces?
So the pace, everybody thinks of a yard as being a pace, but it's not. The pace, the only thing that the pace is actually used for measuring is a mile. So the mile came from actually Roman soldiers. A pace starts on the left foot, goes to the right foot, and back to the left foot. The mile is the distance Roman soldiers marching in formation would march 1,000 paces. So you think about it, left, right, back to left is about 5.28 feet. 5,280 feet is 1,000 of them for a mile. Okay, I'll get back on track. Sorry about that. Voltage. You guys deal a little bit with electricity. Ohm's law says voltage is equal to current times resistance. So if I'm looking at a circuit that has 1,200 ohms and 0.2 amps, the voltage produced, current of 0.2 times the voltage of 1,200. That upside down horseshoe. Have you guys done any electricity yet? Some of you probably have, yeah. That upside down horseshoe looking thing is the symbol for ohms. We multiply the numbers. 0.2 times 1,200 is 240. An amp times an ohm is a volt. So if you ever hear somebody refer to an amp ohm, sometimes they rate transformers. Rather than rating transformers in volts or watts, they'll rate them as amp ohms or volt amps, just because there's just a slight difference in the usage of them. Let's look at power. So there are two forms of power we're going to look at. We'll start out with mechanical. Mechanical power is the work completed divided by the time that it takes. And the time here is typically measured in minutes. So if we're looking at 40,000 foot-pounds or pound-feet of work to be completed in 30 seconds. Now, the first thing we have to be, the reason I put this example in there is one of the things we have to be aware of is the units. The power we're looking at is foot-pounds for work, but minutes for time. So the units on the work, the 40,000 foot-pounds, is correct. The seconds is not. We need to convert the seconds into minutes. Well, how many seconds are in a minute? 60. So when we put this in, the 40,000 foot-pounds will go up here. Now, some of you might notice 30/60ths is half a minute, but you could just put it in as 30/60ths of a minute if you would like. This gets done a lot with lengths. If you have a concrete slab that's 4 inches thick and you're calculating cubic feet, well, you need feet by feet by feet. So you put in, instead of 4 inches of thickness, you put it in as 4/12 of a foot of thickness. So now when you calculate this, if you're going to throw it in the calculator, you need to put parentheses around that 30/60ths. So if you're going to punch in 40,000 divided by the 30/60ths, you got to put parentheses, 30 divided by 60 and close the parentheses, and you get 80,000. Now the unit, a foot-pound per minute, which is what the unit is here, is a watt. Actually, so 80,000 watts is what that comes out to be. Actually, I gotta be careful. We're going to leave it as foot-pound per minute now. We'll do the conversion later. In electrical power, in a circuit, the power is the voltage times the current. Now, you might be looking at it saying, oh, how is that similar to work divided by time? Well, remember, work is a distance times a force, and time, of course, is time. Well, when we're looking at electrical power, a voltage is basically a force. 120 volts, 240 volts, 480 volts, that's the amount of force that the power source is putting behind the current that is flowing through the wires. A current is technically a charge. The unit for charge is usually a coulomb per unit of time. So it's a certain number of coulombs per second or coulombs per minute. So you can see a force times the charge becomes your distance divided by time. That's very similar to your mechanical power. So if we have a 120 volt circuit drawing 8 amps, the power is simply going to be 120 volts times 8 amps. We'll multiply the numbers. 120 times 8 gives us 960. And a volt times an amp is a watt. Again, like I said, there's a lot of transformers that are rated as volt amps rather than watts because it's technically not a power in certain cases. Another one that's very important for you guys, you're going to be doing pumps a lot this semester. Specific gravity. When you're dealing with pumps, head pressure, feet of head, all that stuff, all of your calculations are based off of water or a fluid that is equivalent density of water. So specific gravity is a way to relate any fluid to water. It is the density of actually any substance compared to the density of water. So if I have a specific gravity of 0.5, that's saying that whatever substance we're looking at, if we have an equal volume of water, that substance will have half the weight of that equal volume of water. So if I'm looking at oil, has a density of about 55 pounds per cubic foot. Water has a density 62.4 pounds per cubic foot. So if I want the specific gravity of oil, I'm going to take the 55 pounds per cubic foot divided by the 62.4 pounds per cubic foot. Now you notice here the units are the same, so when we're dividing, the units are going to divide out. So specific gravity is a unitless number. Come on, turn on. So we take 55 divided by 62.4, and we get 0.88. Usually go no more than 4 digits, so we'll go 0.8814 is the specific gravity. Another big formula is energy. So energy is the ability to do work. Remember, doing work means you're causing movement by applying a force. So there are two types of energy. The first is potential energy. And there's technically two types of potential energy. One is gravitational. In old manufacturing, old machining shops, gravitational potential energy was a huge tool. I actually saw a woodworking shop that was set up like this. It was really kind of cool. Had a relatively large weight that was hooked to a small wheel, and the weight was reeled up and set on a shelf, and when they were ready to run any of the machines, they released the weight, and the weight fell, and it slowly turned the wheel as gravity was pulling it down, and that turned a master shaft. They hooked a belt around that shaft to whatever machine they were using. It could turn a table saw, a lathe, whatever they were using, and that's what powered it. So the amount of energy stored is equal to the height times the force of gravity times the mass of the object. Now, typically, we write that as mgh, mass times gravity times height, where gravity is actually a constant. If we're dealing in metric units, it's 9.8 meters per second or meters per second squared. For customary, it's 32 feet per second squared. So if we have a 40-pound mass at a height of 18 feet, I use 32 feet per second squared, but I should note, I believe one of your textbooks, if I remember right, had it listed as 32.2 feet per second squared. It works out the same way, you just have to put in that number. The amount of potential energy is equal to that mass. Now this is pounds, but we're going to go ahead and use it as our mass because in the customary system we tend to do that. 40 pounds times the acceleration of gravity, the 32 feet. Now I'm going to write it like this, per second squared, times our height of 18 feet. So I wrote the per second squared on bottom, so I can set this up as fractions. We'll cover this a little bit more later on when we talk about converting measurements, measurement conversions. But if I look at this, the units are going to kind of fit together. So we have pounds on top here, feet and feet. So feet squared per second. A pound times feet squared per second squared is a unit of energy. So let's see. It's going to be 40 times 32 times 18 gives us 23,040. And again, that's pound feet squared per second squared. We're going to leave it at that for now. The other type of potential energy is called elastic potential energy. And that's what's in a spring. Anything that springs back into shape can store elastic potential energy. If you need bow hunters, when you draw back a bow, that string of the bow is, well, actually it's not the string that's storing it, it's the arms of the bow technically, is storing elastic potential energy. If you let it go, the spring, the elastic pulling it back is going to release energy. Most springs Now, a bow is kind of a poor example because it's not a true spring constant. Most springs, the amount of force that they exert is equal to the distance that it's been pulled from when there's no force on it. It's called its equilibrium or rest state. So it is simply a force times a distance is all that it is for that elastic potential energy. So we do 1/2 times K times the distance. X is the distance that it's been moved from that rest state. K is a property of the spring. It's called a spring constant. The heavier the spring is, the bigger K is. K is the amount of force it takes to pull the spring 1 unit from that rest state or that equilibrium state. So if I have a spring with a spring constant of 0.3 pounds per inch, so that's saying for every inch you pull the spring, it takes 0.3 pounds to move it that far. And it has been displaced 8 inches. The amount of potential energy stored in that spring is 1/2 times 0.3 times 8 squared. So 1/2 times 0.3 times 8 is giving us 1.2. Again, this would be pounds per inch squared is what that's going to come out to be for units. Actually, not pounds per inch. Yeah. Gotta be careful. Pound inches is going to be the units that put on that. Again, we'll go over the unit conversions to get from that to your standard units of energy later on. Another type of energy other than potential is kinetic energy. Kinetic energy is the energy by something that's already moving. So once it's moving, how much energy is it going to take to stop it? So kinetic energy is very similar to the spring energy. It's 1/2 times the mass of the object times the velocity that it's moving at squared. So if I have 20 pounds moving at 120 feet per minute, my kinetic energy is 1/2 times the mass of 20 pounds times 120 feet in 1 minute. So 1/2 times 20 times 120 should give us 1,200. And once again, we have the pound feet per minute. Oh, let's see what other formulas do I want to throw out there. We can look at velocity. Velocity is basically a fancy term for speed, but in a single direction. Velocity is equal to a distance divided by time. So if you have a conveyor that will move a box 1,200 feet in 4 minutes, its velocity is 1,200 feet over 4 minutes. So 1,200 divided by 4 is 300 feet per minute. Any distance unit divided by a time unit can be a unit for velocity. Now, there may be times where we want that in, the feet can be changed to yards or miles or whatever. The minutes can be changed to second or hours. Again, we'll look at how we convert those later on today. Acceleration. So acceleration is a change in velocity over the amount of time it takes to do that change. So one way the formula gets written is like this. That triangle is called delta. Delta V means the change in V, or the change in velocity. All that really means is the initial velocity, the final velocity minus the initial velocity is the change in velocity over time. So let's say we have an object that goes from traveling at 18 feet per second to traveling at 48 feet per second in the course of 6 seconds. Our acceleration, yep, there you go. Our acceleration is simply the final velocity of 48 feet per second minus the initial velocity of 18 feet per second divided by the 6 seconds. Now, if you enter this in a calculator, you can either do the subtraction first, hit equals, and then divide, or if you're going to do it all at once, you got to put parentheses around the subtraction. So 48 minus 18, I'll put in parentheses, divided by 6, gives us 5, and that is feet per second, or feet per second squared. A formula that's very similar to the formula for acceleration is average velocity. And the formula I'm going to use here is for a constant acceleration. If the acceleration is changing during the time interval, the only way to figure out average velocity is to use calculus, and none of us want to go there. So as long as the rate at which the velocity is changing, the acceleration is constant, we can use this simple formula for average velocity. The average velocity, VA, is equal to the initial velocity plus the final velocity. Now up above, remember, for acceleration, it was final velocity minus the initial velocity divided by 2. So up above, we went from 18 feet per second to 48 feet per second in 6 seconds. The average velocity over that is going to be the 18 feet per second plus the 48 feet per second divided by 2. Again, we have to be careful. If I add those, I either put them in parentheses like I did the last time before I divide, or I can just add them, hit equals. Oops, I guess my 1 in the 8. 18 plus 48, hit equals to get 66, and then divide. So we get 33 feet per second as the average velocity. Final formula I'll put up here for now, pressure. So if pressure is equal to a force divided by area. So you guys are dealing with pumps. You're going to deal with pounds per square inch quite a bit. If I have, of course, the abbreviated course is just P equals F over A. So let's say we have a 4-inch diameter hydraulic ram that is holding 1,200 pounds of force. So it's a static ram with a 1,200 pound weight being held up on. Well, the pressure was force over area. Right now we don't have an area. Of course, a ram is a circle. 4-inch means it's got a diameter of 4 inches. we need to find its area before we can calculate the pressure. Anybody remember the formula for the area of a circle? So there's two ways you can find it. It's either pi times radius squared, 3.14 times radius squared, or pi times diameter squared over 4. Now, in mechanical design, in a lot of mechanical areas, you don't get the radius of something, you have the diameter of it. So in a lot of cases, this formula, oops, that's not what I was hoping to do. This formula is easier to use because it uses the diameter. This is the one we all learned in high school and we probably have memorized. Either one is going to work. If it's a diameter of 4, of course, the radius would be 2, right? So the area would be pi times 2 squared, giving us about 12.56 square inches. This one would have given us the same thing. It would have been pi 3.14 times 4 squared and then divided by 4. We'd still get the 12.56. So to calculate the pressure, it's the force of 1,200 pounds divided by the 12.56 square inches. 1,200 divided by 12.56 is 95.54. And that is pounds divided by square inch, so pounds per square inch. Now, I see some of you have a TI-30 calculator sitting in front of you. That's great. That is the perfect one. I see a TI-84. That'll do the same thing. You may have seen here that I didn't type in the 12.56 when I did that second calculation. It says 1,200 divided by ANS. Most of your calculators have a function where you can use the previous answer. So here my previous answer was the 12.56. If I want to use that previous answer, I take my 1,200 and I'm going to divide by that 12.56. Rather than typing back in the 12.56, you can see down here above the minus key, it says ANS. It's probably pretty small print back where you're at. But even on your TI-30, it'll be in a similar spot down by where the equals key is or the enter key. One of the keys down there will have ANS above it. So you hit second and then that key, and what it'll do is it'll use the previous answer so you don't have to type it in. Here, the 12.56 was, wasn't hard. You could type that in and it wouldn't be a big deal. But like the 95.54140.127, that one keeps going forever. If I was going to write it down and type it back in, I have to round it off somewhere. Then we end up with round off errors. So that ANS key allows you to use the exact previous answer in your next calculation. Any questions so far? How's everybody doing? I see some people starting to droop. I realize it's that time of day. We'll take a break here in about another 10 or 15 minutes or so. So let's look at some examples. Let's find the work required to lift 300 gallons of water with density of, so the density of water is about, I shouldn't say of water, I should say of fluid, not water. That's not the density of water that I'm going to put up here. 6.8 pounds per gallon to a height of 18 feet. So it says find the work required. Well, the formula for work is a force times a distance. We have the distance. That's the 18 feet. However, we do not have the force. The force would be the weight of the water. We were not given the weight. We were given the volume and the density. Remember, density is mass or weight divided by volume. To figure out the weight, it's the density times the volume. So we have the density of 6.8 pounds per gallon times the volume of 300 gallons. So in this calculation, the gallons are going to cancel out and give us pounds. So 6.8 times 300 gives us 2,040 pounds. So in our formula over here, the force is 2,040 pounds times the distance of 18 feet. So 2,040 times 18 is 36,720. Again, foot pounds or pound feet, whatever units, whichever way you like to arrange the units. Let's do another one. I'm going to have you try this one in your notes quick. I'll give you a minute or two and then we'll go over it. Find the density of a fluid if 20 cubic feet weighs 178 pounds. I'll give you a minute or so to see what you come up with there, and then we'll go over it. This one's not so bad, right? So technically, density equals mass divided by volume, but since this is in customary units, it's weight divided by volume. The weight of 178 pounds over a volume of 20 cubic feet. 178 divided by 20 is going to give us 8.9, yep. And then, of course, pounds divided by cubic feet is pounds per cubic foot. If we wanted that in pounds per cubic inch, we'll look at that conversion again in our second hour here. Oh, let's do another one. I want to have you try this one in your notes too. This one's going to be a little bit more difficult. Find the power, the mechanical power, required to lift 200 gallons of a fluid every 4 minutes to a height of 36 feet if the fluid density is 7.2 pounds per gallon. There's a couple of formulas involved here. Again, I'll give you a little over a minute or so, then we'll go over it. Get back here. This one might have been a cruel one to throw you into. So the relevant formula is here. We're looking for power. So power equals work divided by time. The amount of work divided by the time it takes. Work is equal to the force applied times the distance moved. We know the distance, but we don't know the force. The force is equal to a weight, and that's going to be the density times the volume. So here we know the time. We need to find the work involved. For the work, we know the distance. We need to find the force involved. So we're going to start here finding the force, which is the weight of the fluid. 200 gallons of fluid with a density of 7.2 pounds per gallon. So it's density times volume, or volume times density, either way, is going to give us what? 14,400 pounds. Perfect. The gallons will cancel out in that calculation. Now we have to get to the work. The amount of work is that 14,400 pounds times the distance given of 36 feet. So we multiply that, the 1,440 times 36, we get work of 51,840. And that's going to be foot-pounds of work, or pound-feet of work. So now the power is the 51,840 foot-pounds or pound-feet of work divided by the time of 4 minutes. So we take the 51,840 divided by 4, we get 12,960 foot-pounds per minute is the power that we need. So if we're in a situation where we need to be able to pump 200 gallons of that fluid to a height of 36 feet every 4 minutes, we need to make sure we have a pump and motor combination capable of that kind of power. Again, we'll convert that into horsepower later. Yeah, that's going to be 16, 17 horsepower, somewhere in there. Let's do one more. Find the power to pump fluid to a height of 26 feet at a flow rate of 80 gallons per minute if the fluid density is 6.8 pounds per gallon. So once again, power is work over time. Work is force times distance. So power is a force times distance over time. Well, if we look at this, we don't have the force times the distance, but we have the right units. The units on power are feet times pounds over minutes. So using those units, we have a flow rate that is 80 gallons per minute. So if I write it like this, 80 gallons per minute, that per minute means per 1 minute. I can turn the 80 gallons into a force using the density. So if I multiply that 80 gallons by 6.8 pounds per gallon, I now have the force for that 80 gallons. And now all I have to do is multiply that force times the distance. It's going to a height of 26 feet. And notice I'm already dividing by the time. The 1 minute time is built into that flow rate of the 80 gallons per minute. So the power when we're looking at pumping a fluid like this becomes the flow rate times the density times the height. So if I multiply that out, 80 times 6.8 times 26, we get 14,144. That's going to be foot-pounds per minute. I think you guys have earned a break. Let's go ahead and take 10 minutes and we'll come back and we'll look at the rest. So we've looked at applying our formulas. Sometimes our formulas don't exactly fit what we're working on. We did this with the density formula. We said the density equals mass or weight divided by volume. But when we needed to find the mass or the weight, we could rearrange this formula and solve it for the mass. This is basically solving an equation. So if I have an equation like, let's put a number in here. 15 equals 3x. And I want to solve this for x. What I have to ask myself is, what has been done to that variable, in this case to x? Well, if I look at this side of the equation, because each side of the equation is separate, what's being done to x there? It's being multiplied by 3. So then what I have to do is I have to take it apart. To take it apart, I have to do the opposite, just like you turn a nut onto it, you take it off, and turn it back the opposite direction. To take it apart, I have to do the opposite. What's the opposite of multiplying by 3? Dividing by 3. So if I divide by 3 here, it cancels out that 3 or removes that 3. But I have to do the same thing to the other side as well. 15 divided by 3 is 5, so I get x equals 5. If I have 7 equals x over 8. Now what's been done to x here? It's been divided by 8. What's the opposite of dividing by 8? Multiplying by 8. So again, if I multiply by 8 over here, it removes the 8. I'm left with x. I have to multiply the other side by 8. 7 times 8 is 56. So 56 equals x, or x equals 56. The same is true even if there are no numbers in the formula. So back up here to the density formula. If I want to solve that for m, for the mass, it is currently being divided by v. The opposite would be to multiply by v. And I have to do the same thing to the other side. So on the right side over here, the v's just cancel out, leaving me with m, or the mass. d times v is just d times v, or dv. And this type of rearranging a formula happens all the time. Now, if I just have, let's say, I want to know how far you can lift 50 pounds while doing 350 foot-pounds of work. So the formula for work, again, is force times distance. Here, we know what the amount of work is. It's 350 foot-pounds. We know what the weight, the force is going to be. It's going to be the 50 pounds of weight. We're looking for the distance. So here the distance was multiplied by the 50 pounds. We're going to divide by the 50 pounds. Again, we have to do the same on the other side. So on the right side, the 50 pounds cancels out, leaving us with just D for the distance. And the other side, yeah, 350 divided by 50 is 70. Pounds divide out, that is 70 feet. So if I were just going to do this once, I would just plug in the numbers like I just did and solve the equation. But let's say I had several different situations where I had different weights and different amounts of work I need to do. I could rearrange that formula so I didn't have to go through the process of solving it every time. If I wanted to solve for the distance, I would just divide both sides by the force. W divided by F is just W over F equals D. And now, rather than solving the equation each time, I could just plug in the weight or the amount of work and the force and divide them out to get the distance. And this happens quite a bit for electrical calculations. My pen's been acting up all day. Voltage equals IR, basic Ohm's law. If I want to know how much current I'm going to have, if I have a 120 volt system going through 8 ohms. Well, again, I could just put in the 120 volts equals I times 8 ohms. And I can divide by 8 ohms. 120 divided by 8 is 15. Now here you'd have to know your electricity. Voltage divided by ohms. If you put volt over ohms, that'd be okay for now. But a volt divided by an ohm is an amp. Over here, the 8 ohms cancels out. I just have I, which is my current. So the current equals 15 amps. Once again, if I'm just going to do this once, that's how I would do it. But if I have to do a lot of calculations to find the current flow for a given voltage and different resistances, this is a more common calculation that you might have to repeat. I would want to rearrange that formula, V equals IR, and solve it for I. So if I'm looking at I, what's been done to I? Well, it's been multiplied by R. So to solve it, the opposite of multiplying by R is dividing by R. So I divide the other side by R as well. V over R equals I is the rearranged formula. Now I don't have to leave it like that. I can switch sides. I can rearrange it. Instead of V over R equals I can write it as I equals V over R. That's the same thing. Then now when I'm giving the voltage, we're assuming we're probably staying at 120 volts. If I'm given a new resistance, let's say at 6 ohms, now rather than having to solve an equation, I can just plug in 120 volts over 6 ohms, and I can divide it out to get my 20 amps. So let's say we want to find the average velocity of an object falling from rest. And here the time to fall is known. So time to fall, again, is just how far it takes from when it starts to when it hits the ground. So falling from rest just means it's stopped, it's not moving. We let it go and it falls. We time how long it takes to hit the ground or whatever surface we're dropping it onto. And we want to know the average velocity. Well, the average velocity is V average equals the initial velocity plus the final velocity over 2. Well, we know the initial velocity is 0, right? Because it's falling from rest. So I can plug that in. This is now 0 plus the final velocity over 2. Well, anything plus 0, of course, is itself, right? So that's just the final velocity over 2. Now there's a formula for velocity is equal to acceleration times time. That's where knowing the time it takes to fall to whatever surface we're dropping it to comes in. The acceleration of gravity is known. It's 32 feet per second squared times the time. So this velocity is going to end up being the final velocity. So we put that in here for the final velocity. So the average velocity of that falling object is 32. I'm going to leave the units off of it. Times the time it takes to fall over 2. In other words, 16 times the time. So not only can we rearrange formulas, we can take one formula and plug it into another formula to get a new one. So here the average velocity of a falling object is simply going to be 16 times the time it takes to fall to the ground. Let's see, what else do I want to put up here? Let's find the final velocity. When the height is known. So the final velocity is easy to find when we know the time it takes to fall. It's just the acceleration of gravity, 32 times the time. But when we know the height, which is typically more common, we know what height we're dropping something from. To figure out what the final velocity is when it hits the surface is a little trickier. To do this, we're going to use our energy formulas. It's called conservation of energy. So we talked about the two types of energy. Really, pen battery's low. I just put a new one in there. Conservation of energy. The potential energy, the energy due from its position in gravity, has to equal the amount of kinetic energy it has from the motion when it hits the ground. When it hits the ground, its height is 0, so there's no more potential energy. It's all kinetic energy. This, of course, is assuming that the object is relatively aerodynamic, so it doesn't have a lot of wind resistance or air resistance as it falls. So the potential energy due to gravity, remember, was the mass times the force of gravity times the height. So I'm going to put in 32 for the acceleration of gravity here. So we'll put the 32 first. 32 is g times m times h. The kinetic energy if you remember, was 1/2 times the mass times the velocity squared. These two things have to be equal. So we know 32 times the mass times the height has to equal 1/2 times the mass times the velocity squared. We're solving for the velocity. Well, the mass appears on both sides. So if I divide both sides by the mass, it just cancels out the mass. Again, as long as the air resistance is very, very small, the velocity that an object reaches when it's dropped from a given height has nothing to do with the weight or the mass of that object. Two objects, one very heavy and one very light, will hit the ground at exactly the same time. So now we have 32 times the height equals 1/2 times the velocity squared. How do we get rid of the 1/2? Well, the opposite of multiplying by 1/2 would be dividing by 1/2 or multiplying by 2. 1/2 times 2 is 1, so that would be just the velocity squared. So 32 times 2 is 64 times the height. Now what's keeping the velocity from being by itself? Squared, right? What's the opposite of squaring something? Square root. So the square root of 64h equals the velocity. The square root of 64 is 8, so we can write that as the 8 times the square root of the h of the height equals the velocity. So if I drop something from 25 feet, the velocity that's going to hit the ground at is 8 times the square root of 25. Well, the square root of 25 is 5. 8 times the square root of 25 is 40. So it's going to be hit the ground at 40 feet per second. Something I worked on at one point was an impact tester where we had a given mass and we wanted it to hit the ground. We wanted it to impact an object at a given velocity. So we were raising it up to a height and releasing it and having it hit a test piece at a given velocity. So in order to find the velocity at the end of a fall, so the velocity at impact, what we really need is to find the height required to get that desired velocity. So we have from up above that the velocity is equal to 8 times the square root of the height, right? If I want to rearrange that for the height, I would divide both sides by 8. So the velocity over 8 equals the square root of the height. And then the opposite of square root is squared. So the square root and the squared cancel out. That's just the height. When I square a fraction, I can square the numerator and the denominator separately. So v squared is just going to be v squared. 8 squared is 64. So that 64, again, is based on the acceleration of gravity, 32 feet per second squared. As long as we're on Earth and not doing anything to alter the force of gravity, the height required to achieve a given velocity is that velocity squared divided by 64. That velocity is in feet per second. So let's say we needed an impact of 40 feet per second. 40 feet per second sounds fast. It's somewhere around maybe 28 miles per hour is really about all it is. So we need a height. We're going to put the 40 feet per second squared over the 64. Now the 64 is actually feet per second per second. 40 squared is 1,600. I'm going to leave the units off of it. Divided by 64. The units are going to come out to be feet. 1,600 divided by 64 is 25 feet. So to reach that final velocity of 40 feet per second, we have to drop our weight, our mass, from 25 feet of height. So let's use this strategy to solve some other problems. Find the pressure at the bottom of a 12-foot tall column of water. So remember, pressure is force divided by area. Force is equal to weight in this case. Well, the weight of the water is going to be the volume times the density. So pressure is usually measured in pounds per square inch. So we want our area in square inches. So let's just define our area to simply be 1 square inch. Notice I didn't tell you how big the column of water is. It doesn't matter. Each square inch of water, no matter how big the area is, each square inch stacks up and gives us a set pressure for the height. So the size of the column, the size of the pipe doesn't matter. It's strictly the height of the pipe that gives us the pound per square inch. But now we need the volume. The density of water is, I remember my density of water. Where is it at? 0.03611 pounds per cubic inch, or 62.4 pounds per cubic foot. My height of 12 feet. So every square inch that's 1 inch tall is going to be a cubic inch. So we need that height not in feet, but in inches. So I'm going to convert my 12 feet into inches. There's 12 inches in 1 foot, so you're exactly right, 144 inches. So that's 144 cubic inches stacked on top of every square inch. So the weight or the force is going to be 144 cubic inches of volume times the 0.03611 pounds per cubic inch. Giving us we're going to go 5.20, we're going to call it, pounds of force. So now the pressure equals the force of 5.20 pounds over an area of 1 square inch. 5.2 pounds per square inch. So again, it doesn't matter how big the pipe is, as long as it's the same diameter or same dimension all the way up. It's strictly the height of the pipe that gives us the pressure, because we can analyze each square inch as a 1 square inch column going up. So this brings us to another concept. Again, this semester you guys are dealing with pumps, talking about feet of head. So head pressure and feet of head are kind of related. It's related to this last problem where a certain height of fluid has a certain pressure at the bottom. So we're going to be talking about water for right now, and an important number for pressure, head pressure, is the height, helps if I can spell, of a 1 square inch column required to contain 1 pound of water. Why is this important? Well, a 1 square, it's really just the height I'm required to create 1 pound per square inch. The 1 square inch column is just saying we're just analyzing 1 square inch of area at the bottom. Water is 0.0, I forgot that number already, 3611 pounds per cubic inch. If it's a 1 square inch column, every inch of height is a cubic inch. So what we need to figure out is how many inches of height it takes to get 1 pound. Well, we're going to take 1 divided by this. That'll give us cubic inches per pound. So 1 divided by 0.3611, 0.03611, gives us 27.69 inches. Now here's where the answer, we don't necessarily have to use the answer key, but here's where keeping this in the calculator helps. Rather than punching back in 26.69, I'm going to leave that in there. I'm going to divide by 12 to convert this to feet. And I get 2.31 feet. In your head pressure and feet of head formulas, you're going to see that 2.31 number come up a lot. What that number is that is the height in feet of a column of water that is required to give you 1 psi of pressure at the bottom of that column. If it's a 1 square inch column, that's the height required to have 1 pound of water in it. 1 pound of water will exert 1 pound of force at the base. So if I'm looking for feet of head, what that is saying is, if for a given pressure, the head in feet is the pressure times 2.31. So if I have a pressure of 20 psi at the base of a pipe, the height of that pipe has to be, again, if the pipe's containing water, has to be 20 psi, so I'll put as pounds per square inch, times the 2.3 square inches per pound. Oops, square, I should say feet per pound. And multiply this out. So our pressure right now is in pounds per square inch. In the formula, I went through it and looked at, do we need to convert that to per square foot? And it doesn't convert out, because remember that 2.31 is for a 1 square inch base. So the units don't necessarily work out on this, but the calculation still does. 20 times 2.31 gives us, oops, what did I do wrong? Oh, 2 times. 20 times 2.31 gives us 46.2. That unit will be in feet. So what that's saying is if you measure the pressure at the bottom of a water pipe, and that pressure is 20 pounds per square inch, 20 psi, the height of that pipe has to be 46.2 feet, or at least the height of the water that's in that pipe. If the pipe is empty above that, there wouldn't be any additional pressure from it. So then if we want to adjust for other fluids, the feet of head is still going to be pressure times 2.31. But again, that 2.31 is based off of water. Remember, we looked back, seems like forever ago, but towards the beginning of the first hour, we had that formula, the specific gravity. It compared the density of one fluid, one substance, to the density of water. And so if we take the feet of head, if it were water, divided by the specific density, or specific gravity, I should say, of our other fluid, it'll give us the feet of head for that fluid. In other words, how tall does that pipe have to be to get that much pressure for that fluid? So if I have, let's say we're going to have 18 psi at the base of the pipe, and the fluid has a specific gravity of 1.18. So it's actually more dense than water. It's heavier than water. The feet of head is going to be the pressure of 18 times the 2.31 over 1.18. Because this is all multiplying and dividing, we don't have to worry about parentheses. 18 times 2.31 divided by 1.18, and we get 35.24 feet of head. Make sense? Clear as mud? Let's do some examples. How far does water need to fall to reach a velocity of 60 feet per second? So this comes into play. I've seen it in a couple places where they actually just use gravitational fall of water for controlled erosion of a material. They can actually use water for cutting materials. Rather than having a pressurized water, they just use gravitational fall. Or if we're just looking for a velocity, like for turning some sort of a water wheel, a power wheel, a turbine of some sort, where you need a distance of fall to get a certain velocity. So how far does it need to fall? Well, we have a formula somewhere for the distance required to get a given velocity. Do you remember what it was? What's that?
Distance and time.
Well, distance equals the height was velocity squared over 64, right? So in this case, the distance is going to be equal to the height. So it's just falling water. So the velocity we need is 60 feet per second. So it's going to be 60 squared over 64. So 60 squared divided by 64, we get 56.25 feet. Find the pressure at the base of a 12-foot column of fluid with density 5.5 pounds per gallon. So the pressure, if it were water, we have our formula, our feet of head equals pressure times 2.31. If I wanted to solve that for pressure, I would divide by 2.31. The pressure equals the head height divided by 2.31. But remember that 2.31 is based on water. So we have to look at the formula that adjusts for that density. So the head pressure, or the feet of head, was pressure times 2.31 over the specific gravity. So if I adjust that formula, solve it for pressure, the pressure is equal to the feet of head times the specific gravity divided by 2.31. How do I find the specific gravity? What's the density of the fluid? 5.5 pounds per gallon. Over the density of water, what's the density of water? 8.34 pounds per gallon. Now I got sloppy, I left the pounds per gallon off, but the pounds per gallon is going to cancel out here. So 5.5 divided by 8.34 gives us 0.6595, we'll call it. So this calculation is the feet of head, which is 12 feet, times the specific gravity, 0.6595, divided by 2.31. So 12 times, I'll just go to the previous answer, divided by 2.31. We get 3.426 about. That's going to be in pounds per square inch. Is our pressure. Oh, let's see here. So we've done a little bit of measurement conversion. Let's talk about doing some more formal conversion. So if I were to tell you guys that I can throw a baseball at a rate of 90 feet per second, how many of you would believe me? One? Yeah, suck it up to the teacher. Is that fast? What units are we used to seeing velocity in? Miles per hour. So I need to convert that into miles per hour. The device that allows us to do conversions is called a unity fraction. You don't necessarily need to know the term, you just need to know the concept. If you go back to second or third grade converting fractions, if I were going to convert 3/4 into 20ths, what we did was we multiplied by 5 to turn the 4 into a 20. So what do we have to do to the top of the fraction? Also multiply it by 5. 3 times 5 is 15. This is called a unity fraction because the numerator is equal to a denominator. When we're converting units, the unity fraction's a little less obvious, but it's still there. If I wanted to convert 3 feet, skip back here, 3 feet into inches. Well, most of us just know that's 36 inches, but if I had to convert it, I could make it 3 feet over 1. Then my unity fraction would look like this. I'd put 1 foot on bottom and 12 inches on top. It's still a unity fraction. The numerator equals the denominator. 12 inches equals 1 foot. And it allows us to convert the units. The feet cancel out. On top, 3 times 12 inches is 36 inches. On bottom, 1 times 1 is 1. So we get 36 inches. So we use that same concept over here. By the way, we knew to put the feet on bottom here because we had to cancel out the feet that were on top over here. I take my 90 feet per second, which really means 90 feet over 1 second. I need to get rid of the feet. Let's do that first. Feet are on top here, so to cancel them out, I'm going to put feet on bottom. And I'm going to convert to miles. 1 mile is 5,280 feet. So the feet have now canceled out. We are now in miles per second. We need to get rid of seconds, so I'm going to put seconds on top. Now we could go from seconds to minutes and then from minutes to hours. I'm going to save a little time and go directly from seconds to hours. Can anybody tell me how many seconds are in an hour? 60 seconds in a minute, 60 minutes in an hour, 60 times 60 is 3,600. You don't have to be scared. There will be a lot of wrong answers yelled out in here. Don't be worried about getting the wrong answer. The seconds cancel out. We now are in miles per hour. So on top, we'll multiply the 90 times 3,600, which is going to give us, I believe, 324,000. There it is. It's 324 miles over, on bottom, 1 times 5,280 times 1 is 5,280 hours. And we simply have to divide that out. So we divide by 5,280. We get 61.36. Not as fast as what you would think it would be. I probably still can't throw that fast anymore. 10 years ago I could, but I'm getting old now. To be honest, if I tried to throw a baseball, I'd probably be in, my shoulder would probably hurt for a week. This getting old thing sucks. I knew I was getting old when I started putting my belt in my pants before I put them on because it hurt to reach behind me. Yeah, you guys, young guys in the room can laugh now. Give it 30 years. So anyway, so before we had looked at some examples. Let me go up and find one of the ones I said that promised that we would convert. Probably won't find it now, huh? It's way up here. There we go. Foot-pounds per minute, that one's. Well, let's look at that one. 14,144 foot-pounds per minute. Come on. Let's see if I have a conversion for horsepower. I should. Yeah. 1 horsepower equals 33,000 foot-pounds per minute. So again, anytime I have a unit like this where it's per something, that per goes on bottom. So this is 1,000 or 14,144. Remember, foot-pounds is foot times pounds over 1 minute. Actually, it'd be easier if I put the foot-pounds per minute on top. Let me leave it that way. Times, I'm going to put the 33,000 foot-pounds per minute on bottom. and that's equal to 1 horsepower. So now the foot-pounds per minute cancel out. On top, 14,144, I don't know where the zero came from, times 1 horsepower is 14,144 horsepower, over, on bottom we have 33,000. If I divide that out, I get 0.428, look out, 0.43 horsepower is what would be required to perform that task. So here's one that always gets people caught up on their first reflex. If I have 6.2 pounds per square foot, and I want to change this into ounces per square inch, I'm going to set my 6.2 pounds over 1 square foot. And this part usually goes okay. I want to get rid of the pounds, so since they're on top, I'm going to put pounds on bottom. 1 pound equals how many ounces? 16. So the pounds cancel out. I now have ounces per square foot. This is the part where I catch people. I have square feet on bottom, so I'm going to put square feet on top. And I want to change it to square inches. 1 square foot is how many square inches? Remember, 1 square foot, what's that?
144.
There you go, perfect. 1 square foot is 1 foot by 1 foot. That's 12 inches by 12 inches. 12 inches by 12 inches is 144 square inches. A lot of people jump in and put 12 in there, and it causes a lot of mistakes. So the square feet cancel out. Here on top we have 6.2 times 16, which gives us 99.2. That's ounces. Over on bottom, 1 times 1 times 144 is 144 square inches. If I divide that, 99.2 divided by 144, I get 0.669, we'll call it, ounces per square inch. If it were volume, that would really get annoying after a full day. If it's volume, by the way, can anybody tell me if I have 3.2 cubic feet? If I want to convert that into cubic inches, I'll put it over 1. I'll put my cubic feet on bottom here. Can anybody tell me how many cubic inches in 1 cubic foot? So when it was squared, it was 12 by 12. If it's cubed, 12 by 12 by 12, right? 12 times 12 times 12 is 1728. So the cubic feet cancels out. It's 3.2 times 1728, giving us 5,529.6 cubic inches. So with this idea of using unity fractions to convert, as long as we have a conversion factor, we can convert just about anything. If I have electrical power, let's find the horsepower of a 100, let's do a 240 volt motor drawing 12 amps. So the electrical power, remember, is the voltage times the current. So that'd be the 240 volts times 12 amps, which is going to be what? 2,880. A volt times an amp is a watt. We want horsepower, so we need a conversion from watts to horsepower. If you look it up, you find that 1 horsepower is approximately 746 watts. You might find like 745.7 or something like that. It's going to work the same if you have a slightly different conversion. So if I take my 2,880 watts, I put it over 1 so I can convert. Watts are on top, so I put it on bottom so it cancels. So 746 watts equals 1 horsepower. The watts cancel out. I have 2,880 on top with horsepower over 746, so I just have to divide. 2,880 divided by 746, we get 3.86 horsepower. So that's going to require a motor of at least 3.86 horsepower. So let's find the power required to we'll do 2 more examples and then I'll get you guys your worksheet. 200 gallons of fluid every 4 minutes to a height of 40 feet. So remember, power is work over time. We know the time. The time's 4 minutes. So this is going to be work over 4 minutes. Well, we need the work. Well, remember, work is a force times the distance. Well, we know the distance is 40 feet. We don't know the force. The fluid, the weight of the fluid is going to be our force. So 200 gallons, we need the density. So it's going to be the density times the volume. So the density of this fluid, I didn't write it down, is 7.2 pounds per gallon. So the weight of that fluid is going to be 7.2 times 200 gallons, or 1,440 pounds. So we put that back in the work formula here. 1,440 pounds times the 40 feet. Gives us 57,600 foot-pounds. So the work is 57,600 foot-pounds. We divide that by 4 to get a power of 14,400 foot-pounds per minute. Now with that, let's find the current draw on a 240 volt motor. Well, we need to convert that into watts. We do not have a direct conversion from foot-pounds per minute to watts. So what we're going to have to do, take that 14,400 foot-pounds per minute. We're going to put it over 1. We're going to convert it to horsepower. 1 horsepower is 33,000 foot-pounds per minute. Once it's in horsepower, of course, this is going to cancel out the foot-pounds per minute. So we'll be in horsepower. Once we're in horsepower, then we can convert 1 horsepower is 746 watts. Once we have watts, then we can put it in our formula to find current draw. So, of course, the horsepower will cancel out. This will give us watts. So on top there, we have 14,400 times the 1, which isn't going to change anything, times 746, giving us a really big number, 10,742,400 watts. Over on bottom, we just have the 33,000. So let's divide out the 33,000 to get 325.53 watts. That's our electrical power. Remember, power is voltage times current. If I solve that, the current is the power divided by the voltage. So I have my power of 325.53 watts divided by my 240 volts. Give us 1.36 amps. Sounds like it should draw way more amps than that, but that's really not a whole lot of power. Have we had enough? Okay. I'll shut off the recording here.